So we're going to pursue now the third part of this AI Spring School. So to make a summary, there is three parts. We were talking about, first of all, with the large pre-trained model updating, and then the diffusion model. And then there was second part this morning also, yesterday at the end of the day, and this morning when we were talking about the generation of multimodal content and the deepfake, but specifically focused on videos and computer vision. And so now we're going to enter on the third, we're going to say, pillar, based specifically on 3D. So at this moment, Mr. Mohamed Daoudi, I would like to thank you because we're going to talk about the 3D human motion generation and the main question for which Mr. Daoudi will try to give us the right answer based on many years of research is that what about the challenging task of human reaction generation, which is focused on generating appropriate reaction in response to given actions. Mr. Daoudi, thank you.
Thank you very much, Jamal. So, good morning, everyone. So my talk will be about 3D human motion generation. And in this talk, I will summarize some of our recent work on 3D face generation of computer graphics. And I will talk also about some work that we have done on 3D human motion generation collaboration with some colleagues for my PhD students. So why 3D human generation? So I think there are many and more applications where we need, to generate 3D human. And I give you here some example of applications, games or social robotic. We have a robot and we would like to interact with the robot in a natural way. And there are also some applications in virtual or augmented reality. And some application also, maybe, I don't know if you know this, we need, like a camera we have in 3D, we have what we call motion capture. But to capture this kind of data, it is very expensive. And we need different of camera. We have, several cameras to capture this motion. And maybe with this new topics, 3D imagination will be able, to generate more and more 3D data without using this kind of camera. So this is some example that we have in my lab. This kind of camera we have, several camera. We can capture human motion, but it's very expensive. It's very expensive. So in this talk, I am going to explain what we did on 3D face generation. But I think this afternoon, Professor Stefano Beretti will explain more better and will give his talk about 3D human body, 3D face. In this part, I'm going also to talk about one work that we have done on 3D face, and with my colleague Sylvain and my PhD student Thomas. So the idea of this work, it's what we call autoencoder. Maybe some of you are very familiar with this. It's very, very old, techniques in deep learning. The idea of autoencoder is given some data like X here. Would like to develop something similar to PCA, but it's non-linear. So the idea is you have two kind of network, one which we call the encoder, another one decoder. And so given the encoder, now given map the space of X here to some what we call latent space, it is Euclidean space. And we have decoder which decode this latent space to another space, this space of X. And the goal here is that when we decode the latent space, the output should be similar to the input. This is what we would like to do. And this kind of network, we apply this kind of network to several applications like compression of image, denoising, image generation. This is in Euclidean space. But what we would like to do is to extend this idea to 3D. And there are several challenges when we would like to do this kind of extension to 3D. So I would like to give a brief description about what is 3D, but I think this afternoon, Professor Beretti will explain more. I explain what is 3D and all the representation of 3D. So this is only for 3D face. There are two kinds of representation. The first one is point cloud. The idea is very simple here. We have 3D face. It is only 3D point into some 3D space. And we can also have a topology, or we can have connection between this 3D face. We can have vertices. It's at some point in the 3D face, and we have a 3D space. And we have the edge which connect this 3D or these vertices, and we can have faces. This is general representation. There are two kinds of representation: point cloud and mesh triangulation. There is, a volume also representation, but it's not, the main contribution of this work. This work we are going to use this kind of representation. And one thing very important in 3D is that when we compare 3D to 2D, in 2D we have some, we don't have the problem which we call parametrization. So we can have the same shape, but with parametrization, it's, the connection between this 3D point can be completely different. But this is the same shape. And this is maybe something very, so this is one challenge when we would like to perform on 3D. On 3D. So this is some challenge that and what we would like to do in this work. So to extend this idea of the encoder to 3D face, mesh, and the face and expression. So and what are the main challenges? The first one, when you compare to the image, the data, it's very hard to collect. This is what I explained in the first slide, that to collect the data, we need a scanner, 3D scanner, and it's very difficult to do this because we need a consuming time. And the second challenge is the set of the meshes is not a vector space, because in the image, we can define image as a vector, and okay, this is a vector space. But in when you work with meshes, it's not vector space. And if you would like to, we want data to live in this Euclidean space, we need to make some processing. And for example, to clean the data and to such that, for example, to have the same topology and etc. So this is difficult, to do. And this is one, there are two challenges. The data is very limited, and the second challenge, the set of the meshes is not vector space. So, okay, now what is our autoencoder? How can we extend the idea of autoencoder when we are working on this kind of data, which is not a vector space? So what we propose is a new autoencoder which is robust to this kind of change, of which we call remeshing, because you can remesh, you change the mesh of the 3D data, such that if you have two kind of meshes, X1 and X2, we would like that encoder, when we encode these meshes, the latent space or the vector on latent space should be equal. Not exactly the same, but we have something is not X1, the encoder of X1, it's similar to the encoder of X2. This is the first thing that we would like. And what we would like also is to train with some training database with different kind of mesh of topology. And this is, there are, I think, few autoencoders which are able to do this kind of training with different kinds of mesh. And what we propose is, our method is to solve this kind of problem is the following. The first one, we have the mesh, 3D face. Now we have a mesh, and we encode this mesh in some latent space. And we decode this latent space, and the output of this decoder is not the mesh, but it is what you call vector field. It's only field. And we add this field to some template. We control the template here. Here, the idea behind it is that the face, there are two information. The face, the first one, it is the identity of the face, and the second information, the expression. So we have a neutral face, and we have what we call a vector field or expression. This is the delta here, correspond to what we call expression of deformation field. So the decoder here, when we encode in latent space, when we decode this latent space, the output of the decoder now, it is the expression of the deformation field. We added this deformation field to some neutral face, which we control, the template. And we compare here the X, the output now, X with the input, and we define a new cost function. A new cost function because when we compare, this is a very big or very challenging problem. When you compare two 3D faces with different kind of topology, it is difficult to do this because if you have the same topology that corresponds between the point, it's very easy. But if you have two kinds of topology, it becomes very difficult to compare that. So we define a new loss function. This is a loss function here. I explain briefly what is exactly this function here. And we define also this autoencoder. It is like asymmetric autoencoder. I mean by this, so the encoder, we have two kinds of network. The encoder here, it is which encode our 3D face or the mesh is based on which a very well-known network. The name is .net, and here we take the advantage to use not the mesh, but use only point cloud. So we have 3D face, we have only point cloud. So we use this .net to encode this 3D information. But to decode now, we use another network which we call spiral net, which which cannot work with we need for spiral net, we need what we call the template. This is very important. Otherwise, we cannot work with this. We have exactly the same topology for spiral net. So what we do is we decode this by using another network, which the name is spiral net, and we decode this. And when we decode with spiral net, we have a deformation field, and we added this deformation field to some neutral phase, which give us some approximation here. It is X, and we compare this output here to our input by using a very special loss function here, which use what we call varifold. I'm not going to explain. If you are interested by this varifold in our representation of the 3D of mesh, you can read our paper. But the idea of varifold here, it's this representation. It's theoretically it is invariant to reparametrization of the surface, and in practice it is robust to remeshing. And we define this loss function such that the outputs of this autoencoder should be similar to the input. And we train with, we don't need to have the same parameterization or the same mesh of 3D phase during the training. And this is what we do. And now we have this kind of network, which based on two kinds of networks. And we can now exploit this latent space. How we can do it? When we have this training, we train our network. We are now able to, to map this 3D phase to some latent space. And as I told you, the advantage of using the latent space, it's Euclidean space. So we can, with this Euclidean space, we can do some. It's very easy, to manipulate because you can have. In Euclidean space, you can find the distance between two vectors. You can perform some arithmetic operation on this latent space. There are many things that you can do with this latent space because it's Euclidean space. It's more easier to manipulate than the space of the surface. So this is what we do. And for example, one example of what we can do in this latent space. So given here, here some the source of the phase. And another, here we have a target of phase. And we can encode this face in latent space. So if we have Euclidean vector, latent space. And we have now another, we can encode this one to some latent space. And we can define the path to go from this source face to this one here. By using a very simple operation, it sees geodesic, in Euclidean space. We have this formula. It's very easy to, to do. This is example of what we can obtain by using this formula here in latent space. Given this one and to go to this one, we can have, as you can see here, we have some deformation here. This deformation to go from this face to this face here. And this is here we have some another example here to go from this one here. This is the same face, and the target here, it's expression of this neutral face here. And as you can see here, I think the deformation, it's called natural deformation to go from this one to this one. And this is some example as you can see here, the animation of this, it's like morphing. If you like to go from one face to another face, instead of working on 3D space, now we can work on this latent space, which is Euclidean space. And we can also do some what you call extrapolation. We can extrapolate, what is the future. So given this is a preliminary result, I think we can do better than what we do here. But this is given two faces. We can extrapolate, what is the future of this this face here. And the last, not the last, but what we can do also, it's neutralization. So given some face here, because we can encode this face in some latent space, it's Euclidean space. We have this face here. We can encode this space in latent space. We can subtract this vector from this vector here. We can add this vector to another one, and we obtain this one here. So we can manipulate with using arithmetic, operation in this latent space. And maybe the last thing that I would like to show you here is the fact that our network is it's robust to remeshing. What I mean is, given this face here with some mesh here, and we encode with our latent space, given another one here, Z2 here, which is another one with some another remeshing here, we can subtract this from this. But as you can see here, we had different kind of meshing, and this is very important. It means that our network is it's robust to if we change the meshing of 3D face. And the result that you obtain here, when you subtract this from this and you add this one here, we can obtain this one here. And all these operations are possible because we are working on this latent space. Otherwise, it's very complicated. Added or to subtract the face or 3D face in the space of 3D face. This is the one work we did, and I think this is there are few works that try to develop this kind of network which is robust to this kind of reparametrization. But the idea here is that we are now able to to interpolate, to extrapolate, and to perform some arithmetic operation in this space. So this is the first part of my work. It's, my presentation is how can we generate 3D face by using this kind of autoencoder. And now the second part of my work, I'm going to talk about 3D human motion generation. And the goal of this work is to generate natural, realistic, and diverse kind of human motion. Okay. So what are the main challenge? The main challenge in this case is human motion is highly nonlinear and articulate, because the body, it's articulate object. And human motion serves as non-verbal communication. So it's if the motion generation is not good, I think we are able to to observe this kind of problem. And the last one is we can generate human motion generation, include the context, including audio, and also the environment of this. So this is some challenge. I'm not going to solve all these challenges in this talk, but some of them, I'm going to explain how we can solve them. So what is hard in this kind of problem? It's the body of a human body is very complex. As you know, there are many things. There are more, it seems that we have more than 600 muscles. It's a lot. 200 bones and 200 joints. It's a lot. So our shape of the body change during the life, our age, fitness, and what we have for the lunch. This is also can have some impact on our body. So we cannot solve all these problems. That's what you assume here. The hypothesis that we do here, what I think our community doing this kind of to analyze human body is to assume that we are only working on the surface. Okay, not we cannot analyze the muscles during the human motion. All this. So we assume that we can observe the surface or what we call skeleton. Okay, this is so. What is which kind of data we are going to use in this kind of human motion generation? What you call skeleton? We have this kind of 3D joint. Okay, we have skeleton. We can also have the surface like this one here, and there are two kind of families of works. Some of them are based on the key point or joint, and some of them, which we call rotation based. I explain very clearly what is exactly this. So for key point based, this is kind of we can collect the data, this kind of data by using like for example Kinect, okay, or for example in some case if you have motion capture system, we can capture the system by using motion capture system. And in this case, what we have only 3D point, okay? We have each joint here, it is here, we have 1 point here, it's, I don't know exactly, the coordinate of this point is 3D point here, and we have some, I don't know exactly how many, point to represent this kind of, this skeleton. And this is what we have here, and the sequence is the sequence of configuration of this skeleton. The second approach, it's based what we call rotation based. One example, very, very important in our approach. It's a simple approach which defined not only by using 3D coordinate, by using more information like rotation, etc. This is very well known in the community of 3D human motion. So now, how can we collect this data? Because this is, as I told you, this is not like a camera. Because a camera, you have your iPhone, you can capture this kind of data, but in 3D it's more complicated. So there are different kind of way to collect the data. It could be we can use like here, this is some example here. We can here with a motion capture system, we can this kind of system, we have this kind of system in the lab, and we can extract this kind of information here. So, oops. Okay, also this here, okay. We can also use like a Kinect or some camera now to extract here some information. There are some new algorithms now that we can use to extract maybe from 2D some information about 3D, but okay, this is, and we can have also some software to, to annotate this data. There are different kind of techniques now to collect the data. It's not easy because collection of the 3D data now sometimes we need more and like this kind of system. So this is a collection of data. And sorry, oops. So I'm sorry, maybe this slide, I don't know if you can read, but the only thing that you can show here is this is a new survey about human motion generation. And what you can see is not, the name of the paper, but what you can see is that since now 2018, there are more and more papers on this topic. And as you can see now in 2000, maybe 2000 and maybe this year, there are a lot of paper on 3D. It seems that this topic now has become very, very hot. There are many, many papers on this. And some of this paper for human generation, they use text. I will explain some example how can we use text to do this. We can use also audio, to generate human motion. 3D human motion, or the sand, but it's not, it's out of, I am going more to explain how text maybe and audio. And this is from this survey. And what we can observe also is that, as I explained, that there are different kind of conditioner to generate this kind of 3D human motion. We can use like a text prompt, and we can generate 3D human motion. Audio, we can have audio or music. You can generate 3D human motion. And maybe our sand, this is a new topic. And there are several kind of methods that can be used to generate this kind of human motion. You can use generative model like a GAN, a diffusion model. I am going maybe to focus more on in GAN and maybe a diffusion model. And the last thing is the motion. Yeah. So this is the approach and the condition that can be used now to generate this kind of 3D human motion. So how to generate this? We are in all these papers, and many papers now they are using what we call, I think now we understood that this is a very important topic now, generative model. So to generate this data, we are using what you call generative model. What is generative model? It's not new. It's very, very old. Since the idea here is to generate like to estimate the density probability or the probability of some data X. Here it could be image, it could be video. I don't know exactly. I don't know who say that. Is that if you are able to given some data like image or video and to estimate the probability, you could be become a billionaire because it's a very difficult problem. And generative model or deep learning techniques, what you would like to, the goal is to approximate this probability. So I explained two of them, which can be used in this kind of problem. So this is the main idea, and the main idea also of this kind of generative model for 3D human motion is to, it's not to replicate what we call training data, but to generate a new data that is realistic. Realistic, I don't know exactly how to evaluate this, but the idea is I explain some criteria that can be used to measure what is exactly what I mean by realistic. So I think this is summarize some of this method used in 3D human motion generation. The first one, I think this morning my colleague Altiza explained the GAN. This is one of them. The second one, it's variational, it's autoencoder, but more statistical autoencoder. And the last one, maybe I will explain, I will explain because we use this kind of diffusion model to generate 3D human motion. This is, I think, the three generative model used in this application of this problem. So the first one, it's like encoder that I explained in my first part of this talk. This is the idea is instead of using a deterministic encoder with latent data space, we have like a normal distribution with the mean and standard deviation, and we can, once we estimate these parameters here, we are able to generate, a new data. The second one, it's the GAN. I think this morning we explained very well what is a GAN. We can use it. And the last one, it is maybe the last one, and this is it's what you call diffusion model that can be used also. This is based on two processes. The first one we call forward diffusion, and the second one is reverse denoising. I will explain later how to use this kind of generative model for 3D human generation. Professor Mubarak Shah explained very well yesterday how to this kind of generative model for image or video. So to compare between them, because it's very important to compare with them, variational autoencoder and GAN and diffusion model, the main difference is that to generate new data by using this kind of GAN or VIO, or variational autoencoder, it is in one step. When you learn your GAN or variational autoencoder, in one step we have the noise, Z, and we can decode, to generate a new sample in one step. In diffusion model, it is maybe a reason why we obtain a very good result if we compare to GAN. It's not in one step, but it is in several steps. And this is the first step. We go from some noise, we denoise, and we explain how to do it. So this picture is very important because it explains what is the main difference between this kind of generative model. So in our case, what we would like to do, in the first part of this work, I explained some state-of-the-art method using only a single person, for generation. And this example here, what we call action to motion generation. The idea here of this is given some action like phone, I would like a phone, and I would like to generate 3D human motion which correspond to this kind of action. And this is a jump. Okay, this is what we call action to motion. So here, we would like to generate human motion, second based only on specific category of action. The second one here, it is text conditional motion generation, given some text, for example, here, like prompt here, and you would like to generate this kind of the man, not exactly here, I can show you after this demonstration here, we can generate this kind of motion given some text here, okay? Text, not action, but text. And another one here, this one here, I can show you this here. So we can, as you can see here, we can have here like a prompt, a person jumping, oops, and we can retrieve, or we can, all the person here jumping. This is what we can do with this action. And for example, here dancing, oops. Okay, this is this kind of thing that we can do. So given some text, some prompt, we can generate, corresponding human motion. And this is sorry, oops. We can also do something similar to this, given some music, like this one here. We can, sorry. This is what we can do with this music. So given some audio, and we can generate dance correspond to this audio. This is another here, some example here. Okay. And so all this work focus only one single person. So the idea of this work is to generate human motion, but it's only for one person. But I'm going on to explain some work that we did in my group. The idea here is not really to focus only one person, but interaction. How to generate the interaction, given something. Okay, I will explain. So this is this kind of interaction that I would like to do. And this work, it's collaboration with Naima, she's here, my colleague Nico Sebe, that we do, and some PhD student, former PhD student, Baptiste. So, and the idea here is the following, the purpose, or what we would like to do, is to the first part of this work. So given some action, for example, if you have in robotic, we have some action, you would like that robot, to react to your action. For example, in one application, in what we are doing, for example, in my group, it's given some avatar. So given some action of human action, you would like that avatar, react to your action. This kind of thing that you would like to do in this work. So given some action, or motion action, we would like to generate some reaction to this. This is what we would like to do. So there are many challenges in this work, but so I think the main challenge here is what I call here coherence between action and reaction. Because when I do some action, I would like that reaction could be something coherent to what my action. Okay. So to do this, there are some challenges. So to take into account this idea of coherence, what we do is when we analyze the action reaction of two person, as I explained in my presentation, that in this case here, what we are doing is we represent human body by using coordinate or joint, 3D joint, okay? And one thing that to be one challenge is during the action reaction, you know, the relationship between this joint in during the action between one given one skeleton here, all these points here or this joint here, they don't have the same relation. This, for example, this one here. It's maybe it's more interesting to analyze the correlation between this point here and this point here. For example, this is an example. During the action reaction between two persons here, what I would like to, for example, to analyze is there is some relation between this point here and this one here, because when you do something, this action here, you have to be careful to this. You have to do some reaction here. So to analyze this kind of behavior during action reaction, we introduce, maybe Baptiste is going to explain more during the lab Thursday, self-attention and cross-interaction attention. We introduce this to take into account this kind of relationship between joint during the action reaction. So our deep network is based on two modules. The first one is what we call the encoder. So the idea here, given some action sequence here, we encode this action by using this idea of which comes from transformer. We encode this information, temporal information, by using this idea of attention. And we have two kinds of attention here, what we call spatial attention. It's between coordinate in one skeleton, and we have what we call here temporal attention. So during the movement or the motion, we have to take into account the relationship between the skeleton during the movement. And once we encode this, what you obtain like a vector which encodes this motion. We have latent encoding here, we encode this motion. And there is another module here, because what we know is that, for example, the joint point here, there is no relation with this one here and this one here. We have like a matrix, what we call adjacency skeleton module. We take into account that there are some, we can define like a matrix which define the coordinate or relationship between this coordinate. This is the first module, and the second one is decoding module. So given now we have the latent encoding of this action here, and we have now reaction, the reaction here. What we would like to do is to define now a new module here, which a motion decoder module here, which decode this information from the first one here. It's the information which comes from our action sequence here, and we have the reaction here. We do the same things. We encode this information of the sequence of reaction, and we decode this information. When we decode the information, we obtain also some here a new or the output here. It is a reaction, and we define the cost function between this reaction here, and the cost function here. We define a cost function between this one and this one. This cost function, it's not very difficult now to define. But the idea is here we have two modules. One is to encode the action. The second one is to decode action and reaction. And we define also two modules, because during the reaction or action reaction, we define which a new module, the distance between the joints. So it's what I mean is that the action reaction, we have to take into account that some joint point between two skeletons could be not necessary, during the decoding. So this is what we define here, and what you obtain is this kind of result that we have obtained in this work. So given here, the inputs, blue, it is the input here, and the reaction, it is here. And this is our network, what we obtain with our network here. So given this action here, this is the reaction of this person. This is the first sum of our result that we have obtained. And this is another here, as you can see here, this is the blue. Blue is our action and the reaction. I think visually the results are not so bad. We have obtained something which is coherent, because during the action of this reaction, it is natural reaction. And we obtain some result also on dance. There is a database which the name is Duty Dance. And the idea here is to generate, action to some, during the dance, we have some action. It is the blue, it is the action, and the red color, it is the reaction to this. And as you can see here, this kind of generation of the dance according to some action of some person. And this is qualitative results, so it's not enough, because visually maybe it's good, but we have to define some measure to measure this. So usually what we define is what you call threshold video distance. The idea of this is not difficult to understand. The idea is to define like a distance between the data which generated by our algorithm, and there is some distribution of this data, and we have the distribution of the ground truth, and we define a distance between them, between this distribution. The name is threshold video distance. It is the assumption here is that this distribution is normal distribution, and it's we can define the distance between two normal distribution. And the second one, it is classification accuracy. So we would like to to compute what is exactly the accuracy of the data generated by our algorithm. And the last one is diversity. Diversity, it means that what we would like is that the reaction, because when you have some action, the reaction could be different. Yeah, my reaction and your reaction, it's not going to be the same. So diversity scores take into account this kind of diversity. Yeah. And this is what you obtain. We compare with many on different techniques, the results that we obtain are very competitive with state of the art. We compare, I think, with more than maybe 6 or 7 methods. I think I remember with Baptiste spent a lot of time to do this this kind of comparison. Yeah, and our method is here. The name is interformer here method here, and I think the result that we obtain, it's very competitive state of the art, and obtain something that we can. Yeah, it's a good result. And the last comparison with by using this criteria of evident diversity, and the same here, we obtain something which is very competitive with state of the art, and we compare with the different techniques. Yeah, I would like to show this because this is some of the last, not our work, but because there are few work on this human interaction generation, and this is some new work that, not this one. I can show you some last comparison between our approach. Sorry.
We see the arm motion synthesized in Remo.
Ramos, it is a new method which the same goal as what we are doing. It's action, reaction generation to action. Sorry.
A learning-based method. We see the synthesizing.
Oops, I show you this. This is, as you can see here. Okay, sorry. Yeah, this is comparison between our method here, interformer here method, and ground truth, and the method Ramos, developed by this team. And as you can see here, this is The results are not bad when you compare our method to sorry, oops, maybe it's very fast here. Sorry. So if you are interested, this is maybe this work is very interesting because there are some good comparison between different kind of CDR. But as you can see here, there are only a few methods that are able to do this kind of generation. And the last work that I'm going to put on my talk is collaboration with Hao Tong and Baptiste. And in this work, Hao Tong is a former PhD student of Nico Sebe. And this work with, it's not the same. There's some goal. What we do here, it's human interaction generation. Here the goal is not to generate a reaction to action, but it's to generate the motion of two persons. Okay? This is what we'd like to do. In interaction using a class level. We have some text, for example, I would like to share and drink, and I would like to generate some action, this kind of interaction between two persons. Okay? This is what we are doing what we do in this work. And there are some challenges. The first one challenge is we would like to some high quality of motion. It's not good, it's not easy. High diversity, because we like to have different kind of human interaction generation. And to do that, what we propose in this work, is to extend this idea of diffusion model to 3D human interaction generation. And this is what I'm going to explain very quickly in here. So I think Professor Mubarak Shah explained many things yesterday about this. But in our case, what we do, I'm going to summarize the idea of what we do here. So during diffusion model, there are two processes. The first one is forward diffusion. It's nothing. It's only we added noise to image. We go from this image here to this image here by adding some noise. There is no training. There is no parameter to learn. But there is another process here. It's a reverse denoising process. During this reverse denoising process, we have to learn some parameters to denoise. So we go from noise here, and we to subtract like the noise from this noisy image here. And to do that, what we do, we have two parts. The first one is training. During the training, I explained very quickly now this idea. So we have the interaction here. The interaction between two persons here. It's 3D. It's not image. It's 3D point, and it is also a motion. It's a motion, okay? And we have the noise. We have the noise. And the idea of this is to predict the noise. We develop some network and the goal of this network is to predict the noise given this this image. So given one sequence here, this is a sequence. Sequence. We have the noise here, and we multiply this by some quantity here. I'm not going to explain all this here in this talk. There are some quantity here that we multiply this. This comes from this formula here. And we have some noise here that we can be multiplied by some quantity here that we have in this formula here. We obtain some noisy 3D human motion here. Okay? This is what I call this by this. And what we would like to predict, it is conditioning by some class. Okay, for example, some text. Okay? And what we would like to is to predict this noise. This noise is the noise, what we call it here, epsilon theta here. And the theta are the parameters of the network that should be learned. Okay? And we have to define this network that learn these parameters to predict this noise. And such that all this quantity here, should be very similar to this noise here. This is what we have in this formula here. This is the loss function that we have to minimize. Okay? We have this minimization to do here. So we have this here, what you equal here, should be very, very similar to this noise. And when you train your network here, when you finish the training, given your network here will be able now to predict the noise. This is what we like to do. And this is what you propose here in this paper. Here we propose a new network here. Yesterday, I think Professor Mubarak Shah proposed to use UNet. This is very familiar neural network using to denoise image. But here it is not image, it's 3D point, 3D coordinate, motion, interaction. There are many challenges to solve in this problem here. And this is what we do. Here we develop a new network, which the name is bipartite graph interaction transformer. It's based on another work that the name is bipartite graph reasoning GAN for personal image generation. We do this, and there are two parts in this work. The first one is how to learn the motion. We have to learn the motion. And the second one, how to learn the interaction. And to learn the interaction, what we do here, we represent the interaction by using a graph. And we learn the graph. This is graph learning. So bipartite graph is based on graph learning. It's a very special graph, but it's based on this idea of to learn the graph. So this is what we do here. But as you can see here, what we would like to, to have like a prompt or like text. Here we have decoder here of the text. And we define this, how to make the connection, or to connect, the motion to this text. We use what I explained very quickly, the idea of cross attention. Thursday, I think Baptiste is going to explain, what is all this idea of cross attention and self attention. And this is the graph. And this is with this network here, we are able to predict the noise. The noise here, epsilon theta. This is our network. And now, given some the process of denoising. As I explained, there are two processes: noising and denoising. So the process of denoising is given some noise here, 3D human interaction. This is noise, and we have this network, bipartite graph here, network. We and given this with denoise, this is okay, and we have this denoising here, and we'd like to denoise this human motion interaction here to go from this one to this one here, okay? And to do this, we are going to use this network that just I defined. But the question is, how can we obtain this denoising, human motion interaction here by using all this and this network? This is what I explained here very quickly here. So given this human interaction here, what we do, there is a formula in diffusion model, this formula here. Given this human interaction, we multiply by some quantity here, okay, here. And we use this, our network conditioning by this, the class or text here to predict the noise. Once we predict the noise here, this is the formula here, when we predict the noise, we can multiply by this quantity here to obtain a new, what you call the mean, here, the mean. This is what you call the mean here. And we added this mean here, this mean, to some standard deviation here, multiplied by some noise here. Okay? This is normal noise. And you obtain now a new or denoising sequence of interaction. This is exactly what we do in this work. And the big picture of this is the big picture of this work. So we have two parts. The first one is the forward process. We know we have the forward process, which we added the noise to our sequence of human interaction. And there is another, process. This is reverse process, given some noise, how to denoise this human interaction to obtain a clean sequence of human interaction. And this is the graph or the network that we are able to predict the noise with this transformer graph. So this is some example of what we obtain here. This is our approach here. And this is what we obtain. This is the ground truth. And this is some example of some method that we compare with. This is our human interaction generation. And this is some other example here of, and this is, the text here is cheers and drink. And this is what you obtain with our approach here. And this is some other technique that we compare with, the motion diffusion and the actor. And the last it's for dance. As I explained, this is also a very interesting topic. Is how can we generate a dance, given some keyword like salsa. I don't know if you would like to generate this kind of dance. It's possible to do this. And this is another example that we can obtain with this method. It is here the keyword is Ramba, and our algorithm is able to generate this kind of dance. So it's not enough, because we would like also to compare to have some qualitative result. Here, this is we are exactly the same with same criteria: threshold video distance, multimodality. To measure the diversity of our data, and the last one is classification accuracy. And what you obtain is very competitive. I think when we compare with some method like actor or motion diffusion, we obtain a very competitive result here. And we compare, we obtain also, as you show here, some result on this data of dance. One important thing is in this kind of generation or this kind of problem, usually what we would like to do is to ask some user, what we call your study. We ask some user, some questions. For example, here, which skeleton sequence is more realistic? We ask them which skeleton sequence match the input text better. This kind of question. And we compare our method with some state-of-the-art method, and I think we obtain a very competitive result here also when we ask the user now to answer to these questions. And this is my last, I think, slide about.
Thank you, Mr. Daoudi. Just one question. Are you real or are you in 3D now? Is there some specific questions you would like to ask for Mr. Daoudi?
Hello. At the beginning, thank you so much for this incomprehensible presentation. And the second, probably I think we can talk. Of course. My name is Hamza Bouslam, a student in Master Big Data and IoT in EMPT. So next week, I think we can talk about a simple approach that there's some studies that going in the current time which stand on the integration of motion to action to motion integration generation with the reinforcement learning. One of the most known one are the integration of action to motion generative with the reinforcement learning for mobile approach, which has been created by Roberto Manhattan and I think Alexander Joseph, which stand on the fact that we can solve the problem of one of the problems that you have presented of that the human integration have a problem of a high quality of motions and that stand on making some random actions and leave the emotions being created based on some environment actions and of course the process of the rewards and punishment. And in the current time, this approach are really limited because of the resources and the performance needed for this kind of learning. And actually, there is some other study that's standing on the fact of make a collection with those with what's called the federated learning also. And thank you so much again for holding this presentation.
Do you have some question? Or I don't understand you.
Just a simple approach.
But I agree with you that here we don't have we need maybe in the future to integrate or, I agree with you. But what is your question? This is a comment or a question?
Just if you have a single idea about the approach that have mentioned integration of model or action to motion generative with the reinforcement learning.
Yeah, I think this is the future, that we have to integrate this kind of idea, yeah. But we don't, here, there is no one from, we don't integrate this there is no, during the action, there is no, the action reaction here, it is very simple. So I agree with you that maybe in the future we have to integrate this kind of.
Yes, because you have mentioned the problem of that we need when we want to make a human integrator or human motions, we need a high quality of motions to make this kind of integration. And people are trying to solve this problem with the reinforcement learning because in this approach we can really make this probably possible.
So one work that we are doing, and I think that this idea, for example, in the when we avatar, we have the interaction with avatar. We need this kind of machine learning techniques, to have more realistic, reaction. Yeah.
Yes. Yeah. Thank you so much.
Assalamu alaikum. As I said, my name is Ilyas Moudni. I'm a PhD student in Ahmadiyya School of Engineering. Let's assume, first of all, your presentation was clear. First of all, let's assume that the test phase of your work is done and is good. Let's move on to the prod phase, or it's like the real stage of your work. It's like the application phase. My question is, did you put in your mind that the lighting condition and it's like the night moment, because I think you will use you will use a camera, and the camera will collect the data, and there is some treatment of those images. Then we will give us like a generative 3D motions, right? So did you put in your mind the lighting condition?
No, in this case, no. We don't have this kind of light condition now. This is what your question. If you introduce this, the light condition, this is your question?
Yes.
No.
Ah, okay.
No, because we, with this camera, I don't know which kind of camera. In the motion capture camera, for example, here, we don't. The problem of light, it's not. We are not using traditional camera here, for example, to capture this kind of 3D data. We are using motion capture, and it's very specific camera for this. This kind of problem, we don't have this kind of problem.
Okay, thank you.
Yeah.
Professor Daoudi, thank you for your presentation. I would like to ask you if you know a method named Gaussian splatting.
Yes.
I think you know.
Yeah.
Is there any possible application of this method to your work?
Yeah, this is completely new. I think it's maybe since 1 year or 2 years.
Yes.
This is, I see that there are some new papers on this, on 3D phase.
Yes.
But I asked my PhD student, to think about this kind of how can we, think, splitting, Gaussian splitting. So it is, the results are very impressive. Yeah, I agree with you that this is a hot topic. Yeah.
Not only for faces, but for 3D environment.
Yes, this is.
They can render really lifelike
yes.
outputs just by having some inputs,
yes.
some 360 degrees inputs.
Yes.
So I wonder if this could be.
I have no work now on this, but we are thinking about it because it's there are many papers on this topic now. It's Gaussian splitting, and this is But no, I don't have. Maybe Mubarak Shah can.
And would you like to have the microphone? Okay. My second question would be for the the reaction avatar, or I don't know how you call it. As far as my modest knowledge is concerned, the only way I think it could be done is to already have an input of a possible behavior of this avatar, and then to, in a sort of if-then-else check, to tell the avatar, it is a kick, so you have to behave like this. It is a handshake, so you behave like this. So I don't know if there is an input of behavioral motion detection that is given to the model to be able to predict, not to predict, but to ask the avatar to behave in a certain way.
What do you mean?
For
You mean
example,
that-
in the example you have given, there is a handshake,
Yes.
a kick,
Yeah.
a dance, and something
Yeah.
like this. I don't know how do you manage to do this.
With avatar. You mean
Yes,
in the
the reaction avatar.
direction avatar, yeah. So we do we have a collaboration with the colleagues who are in psychology, and what we try to do is to learn how human interact.
Okay.
And yeah, this is what we're doing, and given this, we are building some database on this of the human interaction.
Okay.
We try to learn this human interaction, and the idea is when we learn this human interaction, we would like to do something similar with avatar. This is what we are doing. It's not easier problem because it's why this collaboration with the colleague from another department of psychology now, because to human it's more complex, and there's some subtle, it's not easy because sometimes you do something like this. I don't know exactly what is. So all these things, it's why this collaboration with the department of the psychology. Yeah.
And I have two other questions. You mentioned that, for example, the relation or the coefficient of relation between each dot in the body, for example, between the head and the shoulders, and between the shoulders and the arms.
Yes.
It's not the same coefficients.
No, the same coefficients. Okay. Absolutely.
So that's one problem. The second problem is the strength of the movement. For example, if it is a small kick or a huge kick.
Absolutely. All these things, yeah. All these things are the challenge, I agree with you. And this is not, we don't have the same coefficients. It is based on this idea of cross attention and self attention to have the different coefficient for this joint,
And my last question would be, what would be the application of such research? For example, we've talked a lot about metaverse, etc. This could be one application to simulate or emulate a real-life environment, maybe for video games, I don't know.
Yeah, this is what I told you, that one application of this, it is video game. It could be video game. It could be also in virtual reality, to have the avatar to interact with this. And because we have this kind of environment in Lille, I would like to have this kind of interaction, this kind of application. It could be video game because we have some, and also in virtual reality. Yeah.
Thank you very much.
You're welcome.
Thank you.
Yeah, it was nice, interesting work. I think I have seen the single actor, but you guys are doing multiple actors, which is pretty challenging. So one comment I have is once you have these stick figure synthesis, then you can use those to actually synthesize the real video, right? So there was interesting paper called ControlNet in ICCB. They were using the diffusion model, but they were putting the control like canny edge detection, or you can use a depth map or the stick figure, the poses like you have. So I think next thing you can look into getting these generation of these stick figures you have, then you can actually synthesize the real video. And that's what, his question was, that what's a real application? If you can synthesize real video, that'll be very interesting. Yeah. Yeah, okay.
Hi, Mohamed. Thank you for the talk. That was interesting. But I want to follow the questions and comments of the colleague behind me. Because especially when you presented the interaction of the two, of course, the interaction can result in many different solutions, depending on, for example, when you give a kick on the sides of the opponent, on the, how to say, promptness of the opponent in react, and so on. So, in other words, I believe that an interesting solution could be to insert in this process some form of prediction based on some parameters of the 3D avatar. For example, you can decide how prompt is this person to react, how fast he reacts, what is the size of his body, his age, and so on, and have a system that predicts, so that the interaction becomes very much more realistic than fixed as it is.